Welcome to Chapter 18, Thermodynamics, one of my favorite topics, by the way. Okay, we're going to talk about thermodynamics, absolute zero, internal energy, the first law of thermodynamics, adiabatic processes, how this can apply to meteorology, the second law of thermodynamics, orders tends to disorder, entropy, and the third law of thermodynamics. Okay, one of the most important things in thermodynamics is temperature. There are three common temperature scales in use today. There's a Fahrenheit scale, there's the Celsius scale, otherwise called the centigrade scale, and there's the Kelvin scale. Now we're just take some common temperatures here. Freezing point of water, 32 degrees Fahrenheit, 0 degrees Celsius, and 273.15 Kelvin. Now we're going to ignore the 0.15. We're just going to round it off to three significant figures, 273 Kelvin. Normal room temperature, 68 degrees Fahrenheit, 20 degrees Celsius, 293 Kelvin. Boiling point of water, 212 degrees Fahrenheit, 100 degrees Celsius, 373 Kelvin. Okay, so here's some other temperatures, some common temperature. Well, some of them are not so common. Space is about 2.7 Kelvin, slightly above absolute zero. As I mentioned before, we talked about these temperatures here. And of course, we have some other ones here. The surface of the sun, for instance, that's 5,800 Kelvin. That's about 10,000 degrees Fahrenheit. And the surface of a very hot star would be 50,000 Kelvin. That's about 98,000 degrees Fahrenheit. And the center of the sun is about 20 million Kelvin, and that is about 38 million Fahrenheit. So there's some temperatures for you. Okay, now the science of thermodynamics was started in the early 19th century. In those days, they did not really understand atoms or matter, molecules and matters. So early thermodynamics basically just involved macroscopic ideas such as mechanical work, pressure, and temperature, and the equivalent of mechanical work to heat. The foundation stones of thermodynamics are, of course, the conservation of energy, because that's what thermodynamics concerned itself with, and the fact that heat will flow spontaneously from hot to cold and not the other way around. Now, of course, we realize that matter is made up of many tiny particles called atoms, and thermodynamics has been extended into statistical thermodynamics, which is the study of the behavior of large numbers of particles. One of my favorite topics. Now, absolute zero is not Michigan in wintertime, although we have a tendency to say it's colder than absolute zero out there. You can never get it colder than absolute zero. For instance, you have a gas. You put the gas inside a piston, and you keep the pressure constant, and you cool the gas. When you do that, the temperature of the gas will drop, and the volume will also drop at the same time. At 0 degrees centigrade with the pressure constant, the volume will change by 1 over 273 for every degree Celsius. So you can see what happens. You keep dropping this. Eventually, you're going to reach minus 273 degrees centigrade. That's 0 Kelvin. At that point, an ideal gas would have 0 volume. It would disappear. 0 volume and 0 pressure. That puts a lower limit on temperature. You can't have negative volume and negative pressure. We call this lower limit absolute zero. So absolute zero is the lowest temperature, and at that point, the molecules can no longer give up any more heat. You can't get heat out of something at absolute zero. There's no available kinetic energy for them to give up. So you can't cool them any more than that. So that's why that is that way. Now, internal energy. Internal energy is the energy at the particle level within a substance. There are many forms of this, and we put them all together and lump them all together as internal energy. And of course, it gets kind of complicated depending on how complicated the substance is. It can be in form of the motion of the molecules, okay? The simplest form is that just the kinetic and potential energy of the molecules. We're not worried about the internal energy as it is. We're only interested in changes in the internal energy of a substance and what it does elsewise, what it means. Now, the first law of thermodynamics is basically just the restatement of the law of conservation of energy. In other words, what I call the energy law. Energy can be neither created nor destroyed. One of the most important laws of physics, probably the most important law of physics. And it states that the heat added to a system transforms an equal amount of other form of energy. All it says is that energy likes to change form, which is what energy likes to do. Typically, for a typical thermodynamic system, you're interested in the heat, the increase in internal energy, increase or decrease in internal energy, and the work done by or on the system. So heat added to a system equals the increase in the internal energy plus the work done by the system. And that's just conservation of energy. Now, it's an accounting relationship, and you can rewrite that as many ways that there are. The energy in equals energy out plus the change in energy stored is just one example. And this says that there's no such thing as a free lunch. You never get something for nothing. You never get more out than what you put in. In other words, like I said at the beginning of the semester, you want a good grade in physics, you got to do some hard work. You want a better grade in physics, you're going to do more hard work. If you want an A in physics, you're going to do a lot of hard work. You can't do it any other way. Another implication of the first law of thermodynamics is instead of adding heat, if we do mechanical work on a system, we can expect an increase in the internal energy. And that might be a phase change from like solid to liquid or a temperature rise. And you can see this yourself. You can rub your hands together. If you do that, you make friction between your palms of your hands and it makes them warmer. You're converting mechanical work that your muscles are doing into heat. Energy likes to go to heat. It doesn't like to come out of heat, it likes to go into heat. Now, Joule, the same guy that the Joule, the unit, is named for, he decided to investigate the mechanical equivalence of heat. So he built this little device here. It's called Joule's apparatus. It consists of a very heavily insulated container, some water, which he measured the amount of the water, a paddle wheel in the water that can stir the water. The paddle wheel is connected to this crank and pulley arrangement, which connects to two weights here. There's also a very sensitive thermometer in this. And what he did is he poured amount of water, he measured the amount of water, know the mass of the water, he got the temperature, and then he let these fall. And when they fell, they converted the gravitational potential energy through this paddle wheel into internal energy in the water. And that raised the temperature of the water. And by taking all of these measurements, he figured out the mechanical equivalence of heat. And he also figured out that heat is just another kind of energy. They didn't know what heat was. They thought it was some sort of weightless fluid. When work is done on a system, for example, compressing air in a tire pump, it will have a tendency to increase the temperature of the system, or can cause a phase change. In other words, it can cause a phase change from, say, liquid to gas. Now, an adiabatic process occurs when no heat gets transferred across the system boundaries. There's two basic ways you can do that. You insulate the system from the surroundings, so it can't transfer heat either in or out. Or it takes heat time to transfer. So if you do the process so quickly that heat has no time to enter or leave, that's an adiabatic process. An explosion, which occurs very quickly, like the explosion of gas inside a cylinder and piston, that's an adiabatic process to all intents and purposes. When this is true, the heat added to the system is zero. So, and then the only thing that's going on here is the change in internal energy. An increase in internal energy will equal the work done on the system. A decrease in internal energy will equal work done by the system. Example of this, you pump up a bicycle tire using a pump. And when you do this, if you put your hands, do this carefully because it can burn your fingers, it get quite hot. You touch the outside of the piston, that gets very warm. Okay, so you blow air on your hand, first with your mouth, and you want to hold your hand close to your mouth. I don't want to do it in front here because it'll screw up the sound. So you hold your hand within an inch or so of your mouth. Don't let your lips touch your palm of your hand. Blow on the palm of your hand with your mouth open. Then try it same distance away with puckered lips. You're going to notice something. When your lips are puckered, it's cooler. When you pucker your lips, that allows the air to expand as it comes out. And that air, that expanding air, adiabatically does work on the surroundings, and the surroundings will then, it loses internal energy, and that makes it cooler. And you can actually feel that. Now, thermodynamics is very useful in meteorology. I'm sort of a closet meteorologist. I've been an amateur meteorologist since I was a little kid. Why? Because it's all thermodynamics. So it's easy for me to understand. I have lots of fun predicting weather for this reason. And I use thermal to do this all the time. So in meteorology, the first law of thermodynamics is expressed as air temperature rises as heat is added or as pressure is increased. Very simple. Now, how do you add heat? Solar radiation. The Earth will re-radiate heat. Moisture condensation in clouds or maybe snow formation in clouds. And also the ground itself can be warm or the surface of the ocean. Now, in the adiabatic form, that is when no heat is added, the first law of thermodynamics becomes air temperature rises or falls as the pressure increases or decreases. Adiabatic processes in the atmosphere can occur in very large parcels of air. They can be 20 miles across, like in a thunderstorm. Parcels are large, very large, so the outside air doesn't appreciably mix with the air inside them, and air is a pretty good insulator. It doesn't conduct heat very readily. And then they behave as if they're enclosed in giant tissue-tight garment bags. So it's sort of like a huge plastic bag that's very lightweight. When air rises, the pressure decreases. If the pressure decreases, the air expands. And this makes the air cool down. You can get that off the ideal gas law, too. Either one will work. And it will cool down 10 degrees C for every 1 kilometer rise in altitude. So it's sort of easy to remember that. Remember, a kilometer is about 6/10 of a mile. Air will continue to rise and expand as long as it has a higher temperature than its surroundings. And why? Well, if it has a higher temperature, it's less dense. So it's buoyant. It has a positive buoyancy, and positive buoyancy tends to rise. If the air cools off, the density increases, and will have a negative buoyancy, it will sink. So it's a combination, meteorology is a combination of the first law of thermodynamics and also Archimedes. Now, you can form rain clouds by the rapid adiabatic cooling of rising warm moist air. The expanding air cools down 10 degrees C for every 1 kilometer rise in altitude. That's 18 degrees Fahrenheit for every 6/10 of a mile. If the cloud rises far enough so that it cools below the freezing point of water, it will form ice crystals. Now, ice crystals can carry electricity. Okay, they're dry enough to do this. And they're rising and falling. This air is constantly rising and falling in these clouds. And these rising and falling columns of air in the cloud cause the crystals to rub and bump against each other. And that causes electrical charges to build up. And usually the top winds up positively charged and the bottom winds up negatively charged. And charge separation won't exist very long without some sort of discharge. In other words, a lightning bolt. This is called a thunderstorm. And it's sort of interesting. They've only recently discovered that you don't get the lightning stuff. You don't get a thunderstorm until the cloud gets cold enough to form ice crystals. And I always used to say that snow and lightning smell alike. My nose was telling me something there. Okay, now as air parcels drop, their pressure rises because they're going lower in the atmosphere. Remember, pressure rises lower in the atmosphere. And when you increase the pressure on air, it's going to heat up. And this happens out west. You have air that comes off the Rocky Mountains and falls down the side of the Rocky Mountains. This will be toward the western edge of the Great Plains. It can be 10 degrees, and when this wind warm starts up, it's suddenly 60 degrees out, and it's amazing how fast that snow will melt. You go outside and the snow is gone. That's why they're called a snow eater. Now, air will rise and expand as long as it has a higher temperature than its surroundings, because warm air always rises. When it gets cooler, it sinks. Sometimes cooler air will occur at an altitude lower than warmer air. So in other words, the cooler air kind of gets trapped underneath the warmer air because it's more dense than the warmer air. So it stays there. This is called a temperature inversion. Normally the air is colder up above. This is when it's colder down below. That's why they call it a temperature inversion. It's the wrong way. And this can trap pollution near the ground by preventing the normal vertical circulation of air. So air gets trapped and stale. This is dangerous for people with any kind of respiratory problem. You've got asthma or allergies, or maybe you've got COPD. Now, during temperature inversion, the rising warm air is denser than the upper layers of the warm air. It can't rise. Okay, so it can't go anywhere. And you can see this. You ever notice this? You got smoke or something like that, it'll rise a certain amount, and then it hits this temperature inversion, and it can't go any further. And this happens in cities. So smog can get trapped by hot air from the desert coming over the mountains. So this is warmer than this. It's cold from the ocean, and this is hot air from the desert. And this can also happen anytime you have a city that's like in a valley. Cincinnati was famous for these. To see these all the time in Cincinnati. If a parcel of dry air initially at 10 degrees C at ground level expands adiabatically while flowing upward alongside a mountain, to rise a vertical distance of 5 kilometers, what is going to be its new temperature? And remember, air cools at a rate of 10 degrees C for every 1 kilometer. So it's going to be rising by 5 kilometers. So it's going to be 50 degrees cooler than it was before. And it was originally 10 degrees C, now it's going to be minus 40 degrees C. Okay, now the second law of thermodynamics says the heat will never spontaneously flow from a cold object to a hot object. Now, there are many different statements of second law of thermodynamics. I've been collecting these things for years, and I think I'm up to about 30 of them. Example of this, in summer, heat flows from the hot air outside your house into the cooler interior, usually to the detriment of your comfort. In the winter, it goes the opposite way, again to the detriment of your comfort. Now, heat can flow from cold to hot only when work is done on the system. So what you do in order to prevent this, you turn on your air conditioner. And your air conditioner has to be plugged into work because you have to pay for it with energy to pump the heat in the opposite direction. In the wintertime, you have a furnace or some sort of heat pump that makes the heat flow from the cold outside to the warm inside and keeps the inside warm. Now, heat pumps, air conditioners, refrigerators literally pump heat uphill from cold objects to warmer ones. And because they are the reverse of a heat engine and they're pumping heat in the direction it doesn't want to go, it takes energy to do that. You have to do work on the substance in order to make it happen. So these things don't work when they're unplugged. You have to pay for them. Now, a heat engine is any device that converts internal energy into mechanical work. The basic idea behind a heat engine is that mechanical work can be obtained only when heat flows from a high temperature to a low temperature. And in every heat engine, only some of the heat can be transformed into work. The rest of the heat gets rejected as waste heat, which goes into the universe. The universe is a closed thermodynamic system, and it hastens the heat death of the universe. Efficiency is always less than 100%. That's the second law. And not only can you get more out than what you put in, which is the first law, you will get less out than what you put in, which is the second law. And that says the house always takes its cut. The cut is the waste heat. And there's this third law that says there's no way around law number 2. Okay, so here's a diagram of a heat engine. You have a high temperature source, and it will naturally cause heat to flow to a low temperature. And you put an engine in here that will take some of this heat away, divert it, and get some useful work out of it. But there's always some heat that gets rejected. Okay, so a heat engine has a reservoir of heat at a high temperature and a sink at a lower temperature. Every heat engine gathers some heat from the reservoir at high temperature, converts some of this heat into mechanical work, what we call useful work, expels the rest of the heat as waste heat to a sink at a lower temperature, and is never 100% efficient. Heat engines are everywhere. This is what your car engine is like. Here is a steam turbine boiler arrangement. So things like ships' engines and some of the older fashioned steam engines, power plants still have these. Some ships still have these. And guess what? You are a heat engine too, because you burn food, and the heat from the food gets converted into mechanical work and also gets rejected some of it gets rejected as waste heat. Do you realize the person who's sitting absolutely still in a room doing nothing, the waste heat that person is rejecting into that room is about the same amount of heat as an old-fashioned 100-watt light bulb. It's about 400 BTUs an hour. You can run a heat engine in reverse. So a reverse of a heat engine is called a heat mover. And what they do, here's sort of a diagram for that. They take heat from a cold reservoir and they pump it uphill against its heat wants to go from here to here, not from there to there. So you have to do some sort of work to make that heat flow uphill. And plug your refrigerator in. Okay, it turns itself on and it starts pulling heat out of the cold inside of the refrigerator, cooler inside of the refrigerator. And it will pump it uphill, and you can feel the heat coming out. If you put your hand either behind the fridge or underneath it, depending on the kind of fridge you have, you'll feel it get warm when it's running. It doesn't get warm when it isn't running. It's only warm when it's running. That warmth you feel is the heat that heat mover is pulling out of the inside of the fridge. These things always reject heat into the room. This will warm up the room. Now, if you look at here, this heat output, which is this one, is this plus that. So the old-fashioned idea of leaving the door open to cool a room in the summertime won't work. The minute that refrigerator turns on, it's pulling heat out of the fridge, but it has to use work to do that. And this is bigger than that. So when you leave the door open to your fridge, you warm up the room. Also, if you don't have this, if you unplug your fridge, this whole thing stops. So refrigerators don't work if they're not plugged in. Now, what do refrigerators do? They cool off the inside. They keep food from spoiling. They reduce the decay. Decay is entropy, and entropy and decay increase with temperature. You ever notice if you leave something out, something, like milk will spoil faster on a hot day than it will on a cold one? You put food in the refrigerator to reduce the spoilage, and spoilage is entropy. Entropy increases with temperature. Other heat movers are air conditioners and heat pumps, which also pump heat uphill from cold to hot against the natural tendency for it to flow the other way. Now, how do air conditioner works? Air conditioners work exactly like a fridge. There's one difference. You put this coil where the heat gets rejected. This gets moved outside the room. When you do that, the entire room is effectively the inside of the fridge. That's this. As long as this is outside, it will cool that. Okay, if this is not outside of that, when this turns on, it's going to warm this up like that. That's why you don't want to leave the fridge door open. Okay, we can apply this second law of thermodynamics to heat engines. When work is done by a heat engine operating between two temperatures, T hot and T cold, only some of the input heat at T hot gets converted to work. The rest is expelled as waste heat at T cold. So every heat engine expels some waste heat while it's operating. And you can feel this. The exhaust system of your car is warm. The hood is warm. So is the radiator. Those are all places where waste heat's getting rejected. Your breath is warm. You heat up the room you are in by rejecting heat into it. You're like a 100-watt light bulb. That's if you're sitting absolutely still. If you're moving around like me, the more movement you do, the more work you do, the more heat you reject. Second law of thermodynamics says, remember, a lot of times we're interested in efficiency. And the most basic idea about efficiency is what you want divided by what you pay for. The engine efficiency, what you want out of an engine is the work that it does. What you have to pay for is the heat input. In other words, the gas that you buy. Now, the ideal maximum possible efficiency of a heat engine was determined by a guy named Carnot. He used ideal gases, and of course, he assumed that there's no friction in the engine because it's an ideal engine. And it turns out it depends upon the temperature of the hot reservoir and the cold sink. So it's the temperature difference that the engine operates between. Okay, so the ideal efficiency is T hot minus T cold over T hot. This is the Carnot efficiency law. And we can rewrite that as 1 minus T cold over T hot. And it's because this is thermodynamics, it has to be in kelvins. So if they ever give you anything in centigrade, the first thing you probably want to do is convert it to kelvins. Now, efficiency is always less than 1 or 100% for an ideal engine. The only way you can get an efficiency of 1, look at this right here. You want to make this 0 or that infinity. All right, so what happens? You can never get this down to 0 because obviously you can't get anything down to 0 Kelvin. Space is 2.7. T hot, you can't get that to infinity. The last time that was an infinity was when the Big Bang happened. And worse than that, the efficiency of real engines is always less than that of an ideal engine that's operating between the same two temperatures. Typical efficiencies are about 20% for cars and physically fit humans. If you are not fit, your efficiency is even less than that, which is yet another reason to get fit. Large power plants run to about 40%, and you can see why Detroit Edison, they want their power plants as efficient as possible. They want to maximize this, because that's what they're selling you. They want to minimize that. That's what they're paying for. Okay, what is the ideal efficiency of a heat engine that's operating between a high reservoir temperature of 400 Kelvin and a cold sink at about room temperature of 300 Kelvin? Use the efficiency formula and make sure that the temperatures are in kelvins. Okay, so it's 400 Kelvin minus 300 Kelvin divided by 400 Kelvin, 25%. Now, that's an ideal engine. A real engine is going to be less than that. You'll be lucky to get 20 to 15% out of this, and that's between the same two temperatures. Now, let's fix that. We're going to change that engine. We're going to try to improve the efficiency. There are only 3 options when you want to improve the efficiency. You can increase T hot, decrease T cold, or preferably do both. So we have T hot is at 400 Kelvin. Let's increase it to 500. We have a better heat source. Maybe we burn a more efficient fuel, insulate the firebox, something like that. Okay, so now we have T hot minus T cold over T hot, 500 minus 300, 500. It's up to 40%. We've increased it by 15 percentage points. That's pretty good. Now we're going to take our original engine and maybe we can put this in space. We're going to decrease it to 200 Kelvin. So we're going to have to move the engine into space because this is below the standard temperatures on Earth. The average temperature of the Earth is 57 degrees Fahrenheit. Okay, it's about 10 degrees Celsius, which is about 283 Kelvin. Okay, so at any rate, now we're going to do this. Now we have 400 minus 200 divided by 400. It's up to 50%. That doubled the efficiency over the previous engine. That's pretty good. Okay, we're getting encouraged now. Let's see if we can improve it even more. We'll do both. And now we have 500 minus 200 divided by 500. We're up to 60%. That's pretty good. Now, for practical reasons, it can be very expensive to move this into space. For practical reasons, increasing T hot would be the more economical choice. Okay, there actually is a third law of thermodynamics. The third law said it is not possible to achieve a temperature of absolute 0 Kelvin. Okay, we can't get away from the second law. We can never have an efficiency greater than the Carnot efficiency. It also says a 100% efficient heat engine does not exist. Not even an ideal engine can be 100% efficient. So we're going to examine that for a few minutes. For the sake of argument, we're going to assume for a moment that we could achieve 0 Kelvin and use it for a heat sink of an ideal engine. That's the whole point of doing this. So what would happen to the heat sink when we started to dump heat into it? It's going to rise above 0 Kelvin. And as the temperature rises, the efficiency of an ideal engine would fall. On top of that, and we want a certain amount of work output. As the efficiency falls, we have to increase the amount of heat input, which will increase the amount of heat output, which will make the efficiency fall even more. The temperature of the universe is 2.7 Kelvin currently. So we can't even use a universe-sized heat sink at 0 Kelvin because the universe is not at 0 Kelvin. Let's build a 0 Kelvin refrigerator and use that as the heat sink. Yeah, it doesn't work, okay? Because you have to remember it takes work to run a refrigerator, and it has to dump its heat someplace. Okay, so the universe is currently at about 3 Kelvin, so we're going to put our fridge in space. You don't want a huge temperature difference between the inside and outside. Unlike a heat engine where you do like having a large temperature difference, you don't want to have a large temperature difference because the bigger the temperature difference, the harder it is to pump that heat uphill and the more work you have to do on it to get it to go uphill. So you want the smallest temperature difference you can get. So this doesn't sound too bad. It's only a 3 Kelvin temperature difference. But in thermodynamics, there's always a catch. Efficiency is what you want divided by what you pay for. For a refrigerator, what you want is the heat input, what you're pulling out of this cold reservoir here. And what you pay for is the work that you have to pump into this. The refrigerator's heat input divided by work. For an ideal refrigerator, the efficiency is T cold over T hot minus T cold. Well, look at this 0 up here. That means the efficiency of the refrigerator that we're trying to design is 0. That's never a good idea. That never works. We don't want a 0% efficient engine or refrigerator. We can do that. There's 2 ways to get this. The heat input would be 0, but we don't want a heat input at 0. We're trying to use it to cool something. Yeah, we're trying to get the heat here. The other way we can do this is make the work infinity. That's impossible. And it's not certainly undesirable. It takes more energy than is in the universe to run this. And on top of that, we're trying to do this to make our heat engine more efficient. The heat engine will be dumping its waste heat in a refrigerated area, raising its temperature above 0 degrees Kelvin, and the efficiency would drop. Well, this isn't going to work. So you can't get around this. You can't get below 0, and you can't get around the third law of thermodynamics, which means you can't get around the second law of thermodynamics. So the restatement of second law of thermodynamics, one of many, is in natural processes, higher quality energy tends to transform or degrade into lower quality energy as order tends to disorder. So in other words, you can never turn heat completely into useful work. You can always turn useful work into heat, completely into heat, but you can never turn heat completely into useful work. So every time you do anything, any process that occurs will have a tendency to turn useful work into heat, not the reverse. So the entropy of the universe constantly increases, and that is not a good thing. It's called the heat death of the universe. Processes in nature moving from disorder to order do not occur without an external assistance. In other words, energy does this to make this happen. And this always occurs at a cost to the universe because it uses up that usable energy and converts, some of it always gets converted into useless heat. Yeah, right. This heat is what they call a place where energy goes to die. I call it the retirement home. You can't always get it to come back out. Thermal energy is associated with an increased random motion of the particles, which is associated with the increasing disorder. If things are moving around a lot, they have a tendency to become more and more disorderly. Murphy's Law says, left to themselves, things go from bad to worse. If you leave anything alone, you leave your room alone, it gets messier. And of course, if you're in it, unless you're cleaning it up, it gets even messier. A measure of amount of disorder in a system is called its entropy. If the disorder increases, then entropy increases. Entropy can decrease only if work, that is energy, is put into the system. And this energy is the cost that must be paid, and it always increases the entropy of the universe, even more than you decrease the entropy of the small part of the universe that you're trying to fix. So you are a living organism. You take in food and extract energy from the food or from the surroundings, depending on what kind of living organism you are, and you make this you improve your organization. But this decrease in entropy in an organism is more than exceeded by the resulting increase in the universe. Your refrigerator decreases the entropy of the food, preserving it from decay. But that process increases the entropy of the universe even more than it decreases the entropy of the food. You can't win. That's the second law. Third law says there's no way around law number 2. Second law says you can't win. First law says you can't do better than breaking even. The second law says you can't break even. The third law says there's no way around law number 2. Okay, entropy happens to all of us. We age, and that aging is caused by the accumulating damage to our cells by the very processes that we use to convert energy into useful work. You've heard the old expression, we dig a grave with our teeth? Yes, we do, and there's nothing we can do about that. All the health food in the world, all the healthy eating in the world is not going to prevent this process from occurring. We die when our entropy becomes too high, and then we decay, which becomes more entropy. You've all heard about taking antioxidants. When you eat food, you oxidize the food. That very process of oxidizing food causes damage to our cells. And that accumulating damage eventually kills us. It builds up and kills us. A friend of mine always says, if you live long enough, you'll get cancer. Cancer is basically entropy. It's cells that have gone out of control. There is no way out of this. This is the only game in town. The universe itself is doomed to die. We can't get out of this universe. Your locker gets messier every week. In this case, the entropy of the locker is increasing. If your locker became more organized each week, then the entropy would decrease in proportion to the effort expended. In other words, you have to clean it up. And when you do this, you increase the entropy of the universe even more than you decrease the entropy of the locker. Yet another excuse for not cleaning your room. By the way, I tried that on my mom. It didn't work. That didn't work. She said, you still have to clean your room. Just do it more efficiently. That's what it's like to grow up in a nerd family. Okay, a refrigerator cools food, reduces its temperature. Does a refrigerator violate the second law? Well, it does reduce the tendency for decay. It reduces the entropy of the food. Entropy increases with temperature because the thermal agitation equals disorder. So the refrigerator works by reducing the entropy of the food. Refrigerators, though, require an input of energy to work. They don't work if they're not plugged in and turned on. And guess what? They increase your energy bill. You have to pay for the electricity to run them. Refrigerators will reduce the entropy inside their boxes, but they don't violate the second law because they use energy to do this, and that increases the entropy elsewhere in the universe even more than they reduce it inside the box. So overall, the entropy in the universe increases as much by the second law. And guess what? Your refrigerators is contributing to that demise. So the net entropy in the universe is continually increasing, and we call this the universe is running downhill. We say net because there are some regions in which energy is actually being organized and concentrated. and you make ice cubes in your freezer, guess what? That water turns into crystalline ice. Crystals have their molecules all at a fixed location, so they have a very low entropy. But guess what? You had to use energy to do that. And the energy you used increased the entropy of the universe even more than you decreased the entropy of the ice. This also occurs in living organisms. You survive by concentrating and organizing energy from food sources. And you have to do that using energy. If you don't eat, you die. And then you decay. So the decrease in entropy in one part of the universe is always accompanied by an even greater increase in the universe as a whole. And this is called the heat death of the universe. And take a deep breath. You're doing it all the time. And you can't help it. Sorry. The good thing about that is you can't help it. The bad thing about it is you can't help it. Now, the second law of thermodynamics is actually a probabilistic statement. If you took a lot of time, an infinite amount of time, even the most improbable states may occur. Entropy may sometimes decrease. So, for instance, you consider the haphazard motions of the air molecules in a room. They could all spontaneously decide to wind up in the upper right-hand corner of that room, all in a nice, neat little box, all lined up, maybe organized so all the oxygen molecules are on one side of the box and all the nitrogen ones are on the other. So they could all spontaneously do this, but they wouldn't stay there for long because these things are agitating. They're moving all the time. And you would have to wait for longer than the lifetime of the universe to see it happen even for an instant. It's so improbable we can just basically ignore the tiny probability it'll ever occur. Now, these situations are just barely possible, but they're not at all probable. And the more complicated the system, the larger the number of particles, the more improbable they become. And then start thinking how many atoms are in that room. How many atoms are in your body? How many particles are in the universe? Each atom is full of particles. As the number of particles in a system rises, the more likely the system will be in its most probable highest entropy configuration. And the more unlikely it is to be in an extreme low entropy state. Most systems have a staggeringly huge number of particles. 1 mole is 6.02 times 10 to the 23 particles. The sun contains about 1.5 times 10 to the 27 moles, or about 9 times 10 to the 50 particles. That's 9 with 50 zeros after it. The sun is one of 400 billion stars in a galaxy, which in the universe contains at least 400 billion galaxies. And this visible matter is less than 1% of the stuff in the universe. Most of the universe is invisible. It is so impossibly improbable that even our small part of this vast universe will assume a low entropy state that will never happen even in the lifetime of the universe, trillions of years. So you can effectively say that the entropy of an isolated system will naturally assume its highest possible entropy, and it will not spontaneously decrease. And this is true of the universe and everything in it, including us. Okay, so I'm going to pull away from that. We're going to take a block of ice. Ice is cold. It's a crystalline, highly ordered, low entropy solid. Put that on a warmer surface. Warmer surface, higher temperature, faster moving random thermal motion, higher entropy. It's possible the slow molecules in the ice could transfer some energy to the faster moving ones. There's nothing in the first law that says it can't happen, but it's extremely unlikely. It's far more likely for the faster moving ones to bump into the slower ones and transfer energy to them. That will make the ice melt. And as the ice melts, the random motion of its molecules increase, their bonds break, turns the orderly crystalline state into a disorderly random jumble of water molecules. The entropy increases. It does so during any phase change that goes from like a solid to a liquid, or from a liquid to a gas, or a gas to a plasma. Entropy increases because the bonds are breaking and there's an increase in thermal energy and internal energy. So order to disorder. The change in entropy is greater than zero. Entropy increases. Okay, so let's do something else. We'll try throwing a ball at a wall. While the ball's in flight, all its particles, aside from the random motions inside the ball associated with temperature, Small particles have a net motion toward the wall. They're all moving in the same direction. And this kinetic energy can be used to do work. It's useful energy that can be used to do work. It hits the wall in a somewhat inelastic collision, and some of the ball's kinetic energy is transformed into thermal motion. It will raise the temperature of the ball, the roll, and its surroundings. Entropy increases with temperature, so it raises the entropy. The ball rebounds from the wall with less kinetic energy than it had before. This means the energy available for doing useful work, subsequent useful work, has been decreased. An increase in entropy is associated with a decrease in available energy and an increase in the degraded thermal energy, and is less useful for doing work. The entropy of the universe always increases and its useful energy decreases. But the total energy that we have now is the same as the energy that was in the Big Bang. But the useful energy decreases. The word energy crisis always sends me right up the wall. They don't understand that there is no such thing as energy crisis. The amount of energy now that we have now is the same as we had 13.7 billion years ago when the universe was formed. It'll be the same we will have in a trillion years, however, nobody knows for sure how long the universe is going to last, but just for a rough estimate, a trillion years. It'll be the same amount of energy, but none of it will be useful. It'll all be the useless heat that we can't do anything with. When nature is allowed to act without interference, disorder and entropy tend to naturally increase. Disorder is naturally more probable than order because there are many more ways to have disorders. So think about this. It's easier to have disorder than there is to have order. There are many more macro states for disorder than there is for order. There's usually only one way to do something right. There's many ways to do it wrong. Now, you look at this hand here. This hand is a royal flush. There are only 4 possible ways to get a royal flush because there are only 4 suits in a deck of cards. Royal flush is this ace, king, queen, jack, 10, all in the same suit. Since there are only 4 suits, there are only 4 ways to get that. This means it's a highly ordered, not random hand. The entropy is extremely low, and this makes it very desirable and valuable because it's rare. Okay, this hand is worthless. There's at least a million ways in poker to have a worthless hand. Look at that, a million ways here versus 4 ways there. This means this has a very high entropy. It's worthless because anybody can get this, and it's very undesirable in poker. You can't do anything with that one except bluff. Okay, let's throw some dice. We're going to throw 2 dice. Dice are typically 6-sided, and each side will have a certain number of spots on it, like from 1 to 6. And the spots, by the way, are called pips. So we're going to look at all the possible ways we can throw 2 dice, all the different configurations. Okay, a 2, you can only get that one way. That's a 1 and a 1. So there's one possible configuration here. A 3, you can either get that as 1 plus 2 or 2 plus 1. There's a slight mistake there. There are 2 possible ways of getting that, etc. You get to a 7. You can throw a 3 and a 4 and a 3, a 2 and a 5, a 5 and a 2, a 1 and a 6, and a 6 and a 1. There's 6 possible configurations here. You work your way up, go through all of them. There are a total of 36 possible ways that you can throw the dice. So, and any one of these, for instance, a 7, there are 6 possible ways of getting a 7. And the probability of getting a 7 then is 6 out of 36, or 16.7%. And we have another formula for calculating entropy, which we won't go into detail here. Well, we do that in physics 211 and 222. And if you do, there are ways to convert this. And it turns out the probability of throwing a 6, is 16.7. The entropy is 2.47 times 10 to the minus 23rd. This E minus 23 means times 10 to the minus 23rd. Go back to this one here. There's only one way to get a 2. And that means it's only a probability of 1 out of 36, which is 2.78%. The entropy of that is 0. To get for instance, a 9 here, you can there are 4 different ways of getting a 9. The probability of that is 4 out of 36, 11.11. The entropy of 1.91 times 10 to the minus 23rd. Now notice here, the entropy at the least probable ones have the lowest entropy, that is 0. The most probable one has the highest entropy, and that is this one right here. That's a 7. That's why we call that a natural. Okay, so to recap that, with 2 dice, there are more ways to throw a 7, more microstates than any other number. There are 6 microstates there. You can have a 6 plus 1, a 1 plus 6, a 2 plus 5, a 5 plus 2, 3 plus 4, 4 plus 3 for W equals 6 microstates. That's what the W means. There are no other macrostate, throw, has a greater number of microstates, W, a greater probability or entropy. It's the most likely thing to happen, has the highest entropy. By contrast, there's only one way to throw a 2 and only one way of throwing a 12. So both the 2 and the 12 have the lowest number of microstates, the lowest probability, and the lowest entropy. So in other words, you have a greater chance of throwing a 7 than any other number. This is why we call it a natural, because it's naturally the most likely. Now, thermodynamicists like myself do not play games of chance for money because we know better. I call the lottery the ignorant man's tax. Now, and you'll find out why this is in a minute. Everybody knows, you ever hear this expression? You're standing in line and there's a bunch of lines and you have to pick one. Ever notice the other line moves faster? Is that true? That turns out it actually is. Probably. Suppose you have a choice of 4 lines and only one of them can be the fastest. The chance you will pick the best, fastest line is 1 out of 4, 25%. The chance you pick a slow one is 3 times that amount, 75%. So you're 3 times more likely to pick a slow line than you are the fastest one. Chances are that the other line will move faster. With 5 lines, you think, oh, more lines, better chance. Wrong. With 5 lines, your chance of getting fast one is 1 over 5 or 20%. It's actually lower. The more lines or choices you have, the lower your chances are of getting the right one. Now, the next time you look at Michigan Lottery, look at how many games they give you to play. You go to a casino, and they've got machines all over the casino begging you to play them. Humans have a tendency to think that the more choice you have, the better it is. It turns out that is absolutely incorrect. They're fooling you into thinking this is a good thing. Now, take this out of the casino and away from the lottery and think of the many choices you make every single day. Can you see that entropy rules your life on every single level? Yeah. Okay, the lowest possible temperature at absolute zero is 0 Kelvin or minus 273. So both of these are the same, and yes, it is. They both are correct. Which is the smallest, the Celsius degree, the Kelvin, or the Fahrenheit? Well, the Celsius and the Kelvin are the same. And it turns out that there are 5 Celsius degrees for 9 Fahrenheit degrees. So the Fahrenheit degree is the smallest one. For each degree of a volume of air at 0 degrees C is cool. We're assuming the pressure is going to be constant. And of course, cooling means the volume is going to decrease. So you can say you're looking for shrinking. And it's going to be 1 over 273. So it's going to shrink by 1 over 273. Consider a piece of metal of 5 degrees C. If it's heated until it has twice the internal energy, that's twice as hot its temperature will be. Whenever you're doing anything in thermal, you're definitely going to convert to absolute. First thing you do is add 5 degrees C. You're going to add 273 to it and end up with 278 Kelvin. Then you double the Kelvin, and you end up with 556 Kelvin. To convert this to Celsius, you have to subtract 273 again, and you have 283. Now, somebody naive would say 10 degrees C. Always convert to Kelvin, especially when they talk about internal energy and convert doubling the internal energy. Which of these is a restatement of the law of conservation of energy? It is the first law of thermodynamics. In which of these laws do probabilities play a second role? That will be the second law of thermodynamics. Adiabatic processes mainly involve the first law of thermodynamics. The thermodynamics law that applies to meteorology is also the first law of thermodynamics because meteorology usually involves adiabatic processes. A dramatic illustration of adiabatic warming is the Chinook wind. These other two are cooling. As the parcel air is swept upward in the atmosphere, its temperature will decrease. When heat is added to a system, the amount of heat added can do any of these or all of these. When you breathe on your hand, the temperature of the exhaled air depends upon how you blow on it. So be careful when you read this. Always read everything carefully. The second law of thermodynamics tells us the heat does not flow from cold to hot without some sort of energy input. So in other words, your refrigerator doesn't work unless it's plugged in. Heat naturally flows from hot to cold. Heat engines such as a jet engine are more efficient and economical when they are run at high temperatures, which is of course why we burn jet fuel. The ideal efficiency for a heat engine operating between the temperatures 2700 Kelvin and 300 Kelvin is apply the formula, the Carnot efficiency formula. So you plug in 2700 minus 300 Kelvin divided by 2700, make sure they're all Kelvin, 89%. Now this is an ideal efficiency. The real one would be less than that. A soda pop can with a bit of water in it is put on a hot stove. And the water will boil and steam will come from the opening. Steam will fill up the entire soda pop can. And this is a classic demonstration. I've done this myself. Then you take the soda pop can and you quickly invert it into a pan of water. And what will happen is the can will suddenly go like this and collapse catastrophically. I've actually seen this done with a 50-gallon oil drum. It's even more fun with that. What reduced the gas pressure inside the can? Well, it turns out that when steam condenses, it will reduce its volume by 1,671 times. So 1,671 gallons of steam becomes 1 gallon of steam. And of course, when a soda pop can, that air pressure outside is going to be much greater than the pressure inside once that steam condenses and crushes the can. Okay, consider a refrigerator and kitchen on a hot day. If the refrigerator door is left open while it's operating, the temperature of the room is going to increase because the coils where you can feel the heat coming out from are on the inside of the room. If you put the coils outside the room like you do with a room air conditioner or a central air conditioner, then it will cool the room. But as long as those coils are inside the room, the condensation coils are inside, that's the ones that are in the back where you feel the heat coming out of the fridge, then it will heat up the room. Okay, the direction of natural processes is from higher order to lower order, or low entropy to higher entropy, or organization to less organization. As the entropy in a system increases, the energy in the system becomes more and more disorganized or less order. Your room gets messier day by day. In this case, your entropy is increasing. Your mom finally can't stand your messy room, so you clean it up. In this case, the entropy of the room has decreased. Your mom finally can't stand your messy room, you clean it up. In this case, the entropy of the universe has increased. An inventor claims that he has built an engine with an efficiency of 100%. What should you do? Whatever you do, don't send him your life savings. You should just laugh at that. First law says you can't get out more than what you put in. It says you can't win. There's no such thing as a win-win. The second law says you'll probably get out less useful work than you put in. You can't break even. There's no win-lose. If you're very lucky, there might be a win-lose, lose-lose. Third law says there's no way around law number 2. In other words, this is the only game in town. And isn't this a bucket of cheer? Don't you wonder why thermodynamicists are such gloomy people? Well, all right. Okay, well, thank you very much. Please make sure you do your homework, review the book, study your lecture notes, keep on working and doing well.